Hello everyone, today we'll introduce our project, accelerating the Sparse MoE transformer layer on FPGA using the Allo tool. I'm Shenchen, and my group members are Sean, Van Yun, and Tony. I will first introduce the core tool for this project, Allo. It's a Python-based accelerator design language. Its core value is allowing us to build high-performance hardware accelerators using a high-level language, simplifying deployment by adopting a software mindset for hardware design. Allo's strength lies in its full compilation. We start by defining the algorithm and optimizations in Allo Python code. This code is automatically compiled down through MLIR into high-level synthesis C++, which the Vidas high-level synthesis tool then synthesis it into Verilog. This Verilog code is finally converted into the FPGA bitstream, ready for deployment on our target hardware. Crucially, Allo provides a multi-level verification mechanism by utilizing a NumPy golden reference. We can check the design at every stage of the toolchain, including the final validation on the FPGA hardware itself. This guarantees the entire process from Python code to the final FPGA output is numerically sound. Our project focuses on deploying the mixture of expert architecture transformer onto FPGAs to achieve high efficiency. MoE is a sparsely activated architecture where the standard feed-forward networks are replaced by multiple parallel independent subnetworks called experts. The key mechanism is routing. As you can see in the diagram, instead of passing through a single feed-forward network like a standard transformer, the MoE block uses a router to selectively send each incoming token to only a few of the experts for processing. The final result is a weight combination of their outputs. This sparse activation allows MoE to decouple the model's cost from its capacity, significantly reducing the per-token computational load while still achieving trillion-scale capacity and accelerated efficiency. Leading models from companies like Google and DeepSeek now all utilize the MoE architecture to achieve their massive scale and superior performance. Our project configuration is based on the real-world large language model architecture, Google Switchbase 8. We choose this model because it employs a simpler top-1 routing strategy which facilitates deployment, and its parameter count is significantly smaller than models like DeepSeek, which often feature massive parameter counts, making it better suited for our FPGA resource constraints. Considering both FPGA resource constraints and the project timeline, we are implementing and evaluating a 1/8 scaled down version for this deployment.
Okay, so for our Allo model designs, this is our block diagram. And for MoE, we have two more major important parts. One is experts part, and we implemented two MRPVs as our expert. And for the router part, we implement top-K routing layer to flatten our inputs using top-K routing function to select the expert for our input tokens. At first, we just implement MoE and using randomized matrix as an input. But however, we realized that for MoE without attention, inputs are raw embeddings, missing needed sequence contexts. Also, it is unrealistic workload as nobody will run MoE on its own. So we also implemented multi-head attention to serve as an MoE's input. And for our project design, we have like three versions. One is Allo based, which we used our handwritten code like Allo Python to build our layers. And we also have Allo Live, which we use part of the Allo libraries functions like softmax and ReLU. And we also have Allo Alternative, which is the fully optimized attention plus MoE using a mix of Allo library functions, a manual layer implementations optimized with Allo directives. So for our verification, Our idea is like to verify, to make sure our mathematical equivalence between our hardware accelerator and our software baseline. We adopted the differential testing methodology, and we set our absolute tolerance as 5 times 10 to the minus 4, and the relative tolerance as 2 times 10 to the minus 3. And as you can see in the diagram, we will first have our model defined and implement in PyTorch and Allo Python, and we will run through this to get the output from the PyTorch as a reference, and we will also run through the Allo to get the output from the hardware emulation of hardware, and then we will compare them to make sure our implementation matches with what's in the PyTorch. And since we have our design verified, we can start to evaluate our design.
When comparing Allo-base and Allo-lib, from simply rewriting our manual layers with the Allo library functions, we observe close to 7 times speedup. The latency falls from around 380 milliseconds to 60 milliseconds, and the amount of time that the model spends in the MoE layer decreases relative to the amount of time spent in the attention layer. This shows that our MoE received more speedup from these inbuilt functions. Also, using randomized inputs, we compare these models to our PyTorch Godel model and see that the accuracy is 100%. The difference between the outputs between our model and the PyTorch model is on the order of 10 to the negative 7. Additionally, resource utilization stays around the same. With more resource sharing with Allo scheduling, the number of DSPs actually decrease. So now on to some optimizations. In both of these models, the largest bottlenecks were in the experts. Both versions computed the FC layer on all 128 tokens, then stored the output array, then the Gaussian error linear unit on all 128 tokens, and then the output array. So in between every layer, it ran 128 tokens and stored the entire hidden layer. This caused high pressure on the memory bandwidth. So as you see, the fully connected 1 and fully connected 2 both took 3.2 million cycles, and this caused the latency per expert to be more than 6 million cycles. So to optimize, we decided to do row level data flow. So instead of doing all 128 tokens at once, we will do FC1 plus GLU plus FC2 for each token at a time. We also fused together the GLU and FC1 layers with a temp variable and used a buffer between it to FC2 to prevent writing to memory. It then takes around 3K cycles per token, totaling to around 440,000 cycles per expert. We did try to pipeline the outer loop so that we could have token N and FC2 overlap with token N plus 1's FC1 plus GLU, but this caused instruction count and compile time to explode. It would require multiple buffers to have one per in-flight row, as well as multi-port memory access to FC1 and FC2 weights. Thus, we left optimizations at the inner loop. The second key optimization was inside the router. Using the Allo-lib function, the multiply accumulate operations happen sequentially, with experts also sequential. So by pipelining the expert loop and unrolling 4 times the MAC loop, we can increase the throughput of the logic's computation. We notice an increase from 0.125 max per cycle, so around 1 mac every 8 cycles, to 0.28 max per cycle, so 4 max every 14 cycles. Because of the accumulation dependency within this unrolled 4 mac, we do not see the maximum theoretical speedup in the alternative version. Next, onto attention optimizations. In the base version, because of the way our loops are ordered, we were accessing every column, and this is very bad for locality, requiring over 3,000 reads per loop. So by simply reordering the loop, we can keep hitting with 24 uses per read and reduce the number of reads required for every loop to 128. This speedup was provided by the Allo library function, and we went from 3.1 million cycles in the base to 65,000 cycles in the lib and alternative version. Lastly, our QK transpose matrix multiplication loop also benefited from loop reordering. In the base version, there's a loop carry dependency, as the n plus 1 cycle depends on the nth cycle stored y value. The floating point add takes 7 cycles, causing a recurrence II of 7. The Allo library function utilizes a temp register to accumulate values and then only stores at the end of the loop. This removes the store load dependencies and speeds up the loop from 16,000 cycles to 3,000 cycles. While these were only some of the optimizations we implemented to see our max speedup, all other changes followed similar design principles.
As a result, by exploiting HLS optimization primitives and manual kernel design, we are able to achieve a 46.2 speedup relative to baseline and 7 times speedup relative to Allo library, as shown in the tables. That includes performance from on-road max pipelines, and every partition comes at the cost of increased area utilization. In conclusion, we successfully accelerated the attention plus mixture of expert layer using the Allo accelerator design language. Our final results shows a 46.2 speedup relative to baseline and 7 times speedup relative to Allo library. Our model synthesizes and runs on real hardware with the simulation latencies proving close to wall clock. For future work, we would like to do a design space exploration. We can evaluate different number of experts to see if we can scale it to the full Google Switch base 8 model. We can try a lower threshold for verification and evaluate accuracy more rigorously. We can also evaluate accuracy versus latency with different data types. Finally, we can also extend beyond the top K1 routing for improved model quality.
We all really enjoyed making this project, and we hope you enjoyed listening. Thank you.